So there's two real ways, meaningful ways to add complexity to our perceptron model. Up until now, they've basically all been trivial. The change has basically either been in the data or not adding this nonlinearity. So what is this more meaningful changes that we're going to do? Well, one thing we can do is rather than having a bunch of inputs leading to one hidden node, this thing that we were calling Z, we can actually have it feed to a bunch of different ones. Now this picture looks pretty complicated, so let's try to unwrap this. If we ignore these ones here below the green line, then I've got a three-dimensional input, and every time I've got an arrow, I'm going to have a weight. So we're going to feed data into this node here. It's just basically our first observation. Let's change colors here. So we get some value for x1, x2, some value for x3, feed it in, multiply it by a weight. I'm going to have a bunch of weights. So rather than just indexing them with a subscript, I'll have a subscript and a superscript. It's not a squared or a cubed or anything. It's just notation. So this is hidden node 1. So I'm going to call this, let's say, like weight 1, input 1 to output 1. How about that? We'll do that. And what else? If all we had was this one node, we had to do the same thing for x2. That goes into node 1. And we would have to do that for x3. That's this guy here. Oops. Whoa, what happened? W3 into node 1. All right. So, and of course, we're going to add a bias, but I'm running out of space there, so I'm not going to write that. The idea is, for this first hidden node, I'll take every input, weight them appropriately, add on a bias, and hold on to that value for a moment. Now, we're going to do that same exact procedure where we just take our x's and multiply them by weights, x2 by a weight, x3, multiply it by a weight, tack on a bias. But this time we're going to entertain the possibility that we might have a second set of weights that also does pretty good. So I'm not squaring here, I'm just denoting the fact that this is a different set of weights. So basically what I'm doing is now I'm doing this here. Oops. I'm trying to trace in, let me switch colors again. Can I undo that? No, it's not going to let me. Let me switch colors again. We'll go, I guess I'm going to have to go back to, we'll do orange. So when I'm feeding into this second node, where do all these arrows come from? I've got this one here, this one here, and this here. These guys all feed into that node. So each one of those arrows is going to have, and that's what these guys are here, going to have weights associated. Every arrow has a weight implied. Okay, so I've got now two different sets of weights that I apply to each individual row of data. And since I'm weighting these differently, I'm going to get a slightly different aggregation. This is kind of like saying, well, I like people that have these characteristics, and I could weight them this way, but I don't know, some other days I feel like a different set of weights applies. Or maybe my preferences are kind of like a combination of all of those different things. Okay, let's just do one more. We'll get out of orange and we'll try, let me try, I guess I'll do baby blue. So now we'll think about weighting all of our data a third way. So I'm going to get arrows from all three of my inputs. So let's look at our incoming arrows into this blue node. I've got this. I've got here. There's something wrong with my stylus right there. And I've got this right here. Oop, I did it again. Incoming is here. Not this. So each one of these baby blue lines has its own weights. Different weights from before. It's like we're estimating 3 different perceptrons, kind of. And then we do it a fourth way. By now you get the point, but I want to cover up that mistake that I had done. So we have here, incoming from here, and incoming from there. All right, man, that's kind of cluttered, but all right. So this fourth node here represents a fourth way of weighting my 3 inputs. So it's like I kind of have 4 different guesses on whether this person is going to be a match, depending on how I weigh these different attributes. And then what we can do is, well, we still need one outcome. We still need, like, is a person a match or not? Well, all we have to do is aggregate our z's. So we had z, or hidden 4, let's call it z4, and that was baby blue. So we can do a perceptron. We can treat these guys now as input layers into a standard perceptron. So we do z1 times a weight, z2 times a weight, z3 times a weight, and z4 times a weight. Their own weights. Tack on a bias, of course. And then if this is a classification problem, we can say if this thing, if that is positive, predict a 1. If it's negative, predict a 0. If that's classification. If it isn't, if it's just regression, then we were already done. We basically just sum up, appropriately weight our intermediate steps, and we'll come up with an even better guess for our output. That's a pretty powerful thing. Turns out there's a theorem that says that if we're trying to fit a function, any function, like imagine I only had one x just so that I can draw it, and the function was something weird. Imagine like all these are data points. Normally with regression, I'm stuck with a straight line. There's a theorem that says that if I've got a perceptron type model, just one input, but I've got a ton of these hidden layers, and they all spit out to a continuous variable. If I got enough hidden nodes, I can fit any function arbitrarily well. That's a kind of what makes these network models so amazing, is that they can fit really, really complicated behavior fairly simply. Right? We just took, here in this picture, I just took my standard perceptron, and rather than having one z, I have a bunch. And then I aggregate those. It's not too bad. Now, I promise you there are 2 ways for us to complicate perceptrons, meaningful ways. One was adding more hidden layers. The other one was actually adding hidden nodes. The other was actually adding more layers. So this. So here I've got not just these guys that I had before, but I'm actually, with their outputs. But now I'm not just summing them up with their own weights. I'm going to play this game all over again, where I'm going to treat these as inputs going into their own multi-node hidden layer. So we've got basically a sequence of perceptrons, many node perceptrons, where the outcome of one model is the input into the next one. And we can kind of like daisy chain these together and then come up with, here I've got a multi-class problem, but ignore that. We could just have one outcome, and it could be our 0 or our 1, or it could be some continuous y variable. As you can see, though, it is actually pretty straightforward to do multi-class. You just need to allow for, rather than one out arrow, you will have 2 out arrows. So that's its own lecture, but now you kind of know where we're headed with this stuff. We're going to try to develop more and more complicated neural networks to capture more and more complicated behavior. We're in fact going to develop a model that can see and that can actually recognize handwritten characters. We'll actually do this. Turns out it's not that hard. You can even do it in Excel. I'm getting ahead of myself, though. That's just a sneak peek for later. In the meantime, that's it. Be well.